Hello, good morning, good evening, good afternoon, everybody, wherever we might be. It is my great pleasure to welcome Julien Bichon. So, bonjour à tous. Aujourd'hui, nous avons Monsieur le Professeur Julien Bichon, and it will be faithful flatness of Hopf Algebras over Coideal Subalgebras with a conditional expectation. À vous.
Thank you very much. Thank you for the invitation. It's a pleasure to give a talk here. Okay, so I will speak about the topic on the title, so I won't repeat it right now. So the talk, there will be several parts. So the first one, I will recall what faithful flatness is and mostly give some motivation for the concept, which is a bit technical one, but which has some significance. The second part is also some motivation for Hopf algebra theory. After that, I will speak about the question of faithful flatness over Hopf subalgebras and survey a bit what is known and what is not known about that. I will go then to a slightly more general framework, the setting of Coideal subalgebras. And then the last two sections are about the proof of the result I want to present. Okay, I will give the main ideas. Okay, so what are we talking about? Faithful flatness. So let's consider an algebra A. So we always will be over the field of complex numbers. It's not necessary, but it's simpler in particular for examples. So let's not, okay, let's be in this framework. So consider a right A module M. So it is said to be flat if the following functor here, the functor from left A modules to vector spaces over C, which you take a left A module X, you tensor on the right by M is right. So you can do that. You get a vector space without more structure if you don't have more structure on M or on X. Okay, so this is a functor, and you can consider the question whether if it is exact, namely if it preserves the exact sequences of modules. And okay, exact in the usual sense. Here, all the categories I consider are concrete categories, so exactness is really what you can imagine. The kernel of a map is the image of the other one on the left. So okay, and okay, so that's for flat. And there is the strongest property of faithfully flat. So you ask that M is flat, so M preserves the exact sequences and also creates them, which means that if you take a sequence of left A modules, the original sequence is exact if and only if the new one obtained by tensoring, by applying your functor, is exact. Okay, so it's stronger than flat, and it's often the more useful. Okay, so this is a perfectly natural concept, but you really can put this definition. But why is it interesting?
Sorry, Julien, just a quick jump in. Can you go back to the previous slide, please?
Oh, yes, I can.
If I remember Bourbaki correctly, you also have a concept of a module which is just faithful. And then there's this sharp curve, you know, this Bourbaki sharp curve, which says that you can have a module which is both faithful and flat, but not faithfully flat.
Yes. So
that's kind of tricky, yeah. And
yes.
And another thing which is tricky, well, you can prove that every finitely generated projective module is faithfully flat, but there is an example in Bourbaki of a module which is projective, not finitely generated, which is not faithfully flat. Do I remember it correctly?
Oh, maybe I don't think. No, I think the example, the complicated example, is that you to have a faithfully flat example which is not projective. I think that you refer to that.
Okay, maybe.
I think that projective is always faithfully flat.
Okay.
So it's close to projective. I will.
Yeah.
It's one of the motivation to study it. Okay. So again, it's natural from the categorical viewpoint to consider that, but the success for the notion comes from algebraic geometry, of which I'm not at all a specialist. So don't ask me too complicated question. But here is the most simple illustration of the use of faithful flatness. So you consider an extension of commutative algebras. Okay, and if the extension is faithfully flat, which means that B is not flat, faithfully flat as a module. So here you can consider on the left or on the right, it's not, you're in the commutative setup. So you have the following map because of the extension. You consider an algebra map from B to C, and then you can restrict it to A. In general, there is no reason that this is surjective, even if you have an inclusion. Okay, but if it's faithfully flat, the corresponding map is always surjective. So this is some kind of notion for surjectivity in the dual setup. So in geometric situation, A, B are coordinate algebras over affine algebraic varieties. And so this gives you, in some sense, a good categorical notion for surjectivity. In general, you have categorical notion corresponding to injectivity or surjectivity, monomorphism or epimorphism, but it doesn't correspond exactly. And here, in some sense, it tells you that it's a good condition for surjectivity in the dual setup. Okay, and more generally, if you assume that your extension is flat, it is faithfully flat if and only if the corresponding map on maximal spectrum is surjective. So it's something interesting from this viewpoint, from the viewpoint of surjectivity. Okay, so from this you have an easy example of something which is not faithfully flat. Consider the polynomials in one variable. So it naturally is a subalgebra of the Laurent polynomials, where you just invert your variable. And this is not faithfully flat because the corresponding map on the spectrum is the natural map from C star to C. Okay, and clearly this inclusion is not surjective. Okay, so that shows you that this is now an example of non-faithfully flat stuff. Usually you expect things to be faithfully flat. And so another example in the same spirit, if you take the coordinate algebra function on SL2C, so this is subalgebra generated by coordinate functions. And then it has as a subalgebra CXY, let's say that it corresponds to the function on the first line or the first column. And this is not faithfully flat because at the dual level, the map from SL2C to C2, which just forgets the second column, for example. This is not surjective because you can't reach 0, 0 with this map. Okay, so yes, so that illustrates this claim that faithfully flat is a good notion for surjectivity on the dual level. Okay, so that's really a simple motivation, a bit more sophisticated, but in the same spirit of ideas. This is faithful flatness is responsible for the existence of a good quotient theory for algebraic groups, affine algebraic groups. So yes, in fact, the faithful flatness of a commutative Hopf algebra over its Hopf subalgebras, we will come back on later on that, is a key ingredient to show the following fact, that if you take an affine algebraic group, so group defined by polynomial in JULIEN, defined by polynomial equations, and if you take a normal affine algebraic group, subgroup, then the quotient group that you can do set theoretically, but you have, it's not obvious that it will be again the solutions of a set of the zeros of a set of polynomials. But it is, and to prove that, you really use this faithful flatness stuff. So Okay, so the general philosophy is that faithful flatness is important question for notion for cushion theory. Okay, and another motivational fact, we have already said it, that projective implies faithfully flat. So very often we are interested maybe more in projective modules for many good reasons in homological algebra. And okay, so projective is always stronger. But there are circumstances where the converse is true, and generally it's hard to find examples where it's not the converse is not true. So
a quick question: when you have this counterexample, when you have a module which is faithfully flat but not projective, is it a commutative example? I mean, the ring is commutative or not?
yes. I think so. If it's in Bourbaki, it's like it's the commutative algebra book, and so
Okay.
I think these are commutative.
Okay, you are right. Yes.
Okay. So, and now the second topic I will speak about, the theory of exact sequences of algebras. Also, we will see that it's really, when we know that we have faithful flatness, it simplifies the setup, and that's another motivation. Okay. So I have not assumed that everybody, I assume that you have met Hopf algebras, but maybe most of you are not really specialists. So I will do a quick reminder of what Hopf algebra is. It will be very quick. So if you, okay. So Hopf algebra, it's an algebra with three algebra maps. Okay, so if you think as an algebra, as a function algebra, so there is this co-multiplication, which corresponds to a group multiplication on your set, the co-unit, which corresponds to the unit, and the antipode, which corresponds to the inversion. So it's really, if you think of algebras in terms of function algebra, an additional structure that makes you something like a group. Okay, and there are actions. Of course, you can't just give this stuff without action. So co-associativity, it's associativity of the dual law. Co-unit, it's you have a unit element, so you have actions, and the antipode action, it's some kind of inversion. It's inversion for the group law. Okay, so yes, we have all this structure, but you have to if you think as an algebra as a non-commutative space, so the additional axiom is what you get is what you need to get some kind of group. Okay. Okay, so there are plenty of examples in nature, and it unifies the numbers of a number of things. So already I mentioned algebraic groups. So you take the algebra of polynomial functions. This is Hopf algebra. This is an algebra, and the co-multiplication and so on are induced by the group law. Okay, so if you're more like, if you prefer topological groups, if you consider a compact group, okay, let's say, and you consider the algebra of representative functions, so these are the coefficients of finite dimensional continuous representations. Okay, it's also Hopf algebra, and again, really it's always an algebra. It's an algebra, and the co-multiplication and so on come from the group law. Okay, so these two kind of examples are very close in spirit, but you have completely different stuff with group algebras. So you take the vector space linearly spanned by a group. You can see it as function. Also, maybe it's better to see it just as formal, the formal vector space spanned by the group. Here, it's an algebra because of the group law, and it's the co-multiplication. It's what marks the elements of the group. You declare delta of an element of the group is, if you call it X, it's X tensor X. Okay, so here you use the Hopf algebra structure to mark the group element. Okay, and also a famous classical example is the enveloping algebra of a Lie algebra. very different than the third free one, but it's also an example which occurs in nature. Okay, and still in nature, there are many, all these examples come from classical theory, but of course, there are many examples where the algebras are not commutative or not co-commutative. And of course, the most famous one are the quantization of Lie groups, so OQJ, so okay, the same spirit as that, or UQJ, deformation, in some sense, of the enveloping algebra of Lie algebra. Okay, and usually Hopf algebras serve as quantum symmetry groups in non-commutative algebra and geometry. You use them to describe the symmetries, kind of symmetries of non-commutative spaces. Okay, so that it's already, if you take the classical examples, unifying them, unifying enveloping algebras and group algebras is something which is not easy, and it's clearly you have very general object. Okay, so I've given this rough definition, and now I go a bit more into some things that are more technical, but I want to define exact sequences. So I did not define morphisms, but it's kind of obvious. It's algebra maps which preserve the co-multiplication and the co-unit. So, okay. So now, what should be an exact sequence of Hopf algebras? So I give the definition just after, but before that, I need some bit of notation and things. So if you start H a Hopf algebra and A Hopf subalgebra. So this means it's subalgebra and stable under the co-multiplication and antipode. So take A plus, this is the kernel of the co-unit, intersected with A, and consider, so I don't see it really well, but it should be, oh, there is a mistake here. It's not AH plus, and so this one, A plus H, it's okay. It's a right H module, a sub-H module spanned by A plus, and here this should be A plus H. Oh, sorry, no, it's okay. It should be H A plus.
It's not kernel of epsilon of co-unit in algebra A.
Sorry?
It's not kernel subalgebra of A. It's not epsilon defined on A. Why you intersect with A?
I intersected with it's yes.
Because
you can define it as the kernel of the co-unit restricted of A.
Okay, so we have some subalgebra. Okay.
Yeah.
Okay, sorry. Thanks.
Okay, so you take these two kind of thing, A plus H and HA plus. Here it's written correctly. Okay. So here, and it's not automatic that you have this equality here, but when you have it, so it's some kind of normality. It looks like normality. Then this is of ideal, which means that you can give the definition, but if you make the quotient, there is a Hopf algebra structure on the quotient such that the canonical surjection is a Hopf algebra map. Okay? So when you have this condition, you can create a quotient, just like the normality condition for groups to make the quotient.
If you don't mind me jumping in again and reminding a very famous example, it's of Podley spheres. If you want to see the Podley spheres as fixed point subalgebras, under UR action, or if you want, coaction of an appropriate Laurent polynomial of algebra, then for the standard Podley sphere, you have exactly this normality condition satisfied, okay?
Yes.
But for generic ones with A plus H is not equal to H, A plus, and you choose your left or right thing, and then it's only a coalgebra, but you can still find coaction invariant subalgebra, and this gives you a generic Podley quantum sphere.
Yes, absolutely. Here I consider of subalgebra, which the Podley sphere is not. But
of course, yes, of course.
But we'll come back. We'll speak about Coideal subalgebras after. But you're true that you can have interesting thing even if you don't have that. I agree. But if you want making a quotient and get a Hopf algebra, this condition is natural.
And because it was a very natural problem, because Podlesh defined his spheres not as fixed points of algebras. So if I remember correctly, it was Brzezinski who solved it, maybe Brzezinski Majid, to find, to prove somehow in what sense the generic Podlesh quantum spheres come as, quotients from SUQ2. And then this whole Algebra-Galois theory was discovered. I mean, maybe it was already discovered earlier, but then it got a lot of impetus because this was a manageable example. It's already non-trivial, but it's still calculable. You can do calculations.
An example where you can see something, yes.
Exactly, yes.
Okay, so, and my second concept is, it's really related to the Podlesh sphere. If you take a surjective morphism of algebra, Pim from H to L, then you can consider two subalgebras of coinvariance, which corresponds to some kind of cosets. Don't ask me which the one is left or the one is right. Okay, but you have the one on the right, which seems to be on the right, where you write coel on the right, and so you okay. Thank you for the. And so with this condition, you apply delta. And then you apply your projection on the right, and you ask to have X tensor 1. So this is some kind of right or left coset space. And you can do this exactly on the left. Okay. So Podlesh sphere, it's defined thanks to the projection of OSUQ on KZ, or okay, the torus, or OT. Okay. And so you have these two subalgebras which do not coincide in general. But when they coincide, this is a Hopf subalgebra of H. Okay, so this condition is also a notion of normality for a surjective morphism of Hopf algebra. So you have the question whether you have this condition, which is not automatic. Okay, and so we arrive with the notion of exact sequence. So I take the most symmetric possible actions. So, okay. So a sequence of Hopf algebra map. So you have I from A to H and P to H to L just as before. I can be just the inclusion. And this is said to be exact. Of course, you ask E injective and P surjective. And then you ask that the kernel of P is H EA plus, and this must be equal to IA plus H, and then the coinvariance on the left and on the right must coincide with IA. Okay, so if you want to work in there is no reason to prefer the second condition of the third. The natural thing is to impose both, because you don't have to really some kind of algebras should be some kind of category with duality. So you should not prefer one sense or the other. So the natural thing is to ask for both. Okay, and so we have this definition, and then fortunately it coincides with the usual one for discrete groups. Take a sequence of discrete groups, then you have a sequence of algebras of these discrete groups, and the sequence is exact if and only if it is exact in this sense. Okay, with all these conditions, we will see that in fact there are some actions which follows from the other in this case, and as well as the second example. Take a sequence of morphism of affine algebraic groups or of compact groups. It works the same. Then the sequence is exact in the usual sense. The kernel of the map from N to G, the image of the map from A to G is the kernel of the projection from G to H. If and only if the corresponding exact sequence of algebras is exact. Okay, so at least the notion generalizes what the concept that we know. Okay, so now we have the definition, we have the basic classical examples. Hop. And now how to construct the exact sequences. Of course, just as you do with group, you can either start with a normal subgroup, make the quotient, or start with a quotient map and consider the kernel. So here, let's do it from the viewpoint of normal subgroup. So you start with the Hopf algebra with your condition, your normality condition here. And so we said that you can consider the quotient map. So you would like this to create, to be an exact sequence. But you still have to check this. And why is it interesting to know that your extension of Algebras is faithfully flat? Because this solves in this case. This solves if you know that H is faithfully flat as a left or right A module, then you know that that you have really an exact sequence. Okay, so clearly it's this condition to check. It can be a really unpleasant, I think, and so it's good to be able to avoid it. Okay, and on the dual level, if you start with a surjective morphism of algebras, which with the normality condition, just like that, A, so this algebra of coinvariance on the left or on the right is of subalgebra. And then again, same problem. You have to, if you come back to your definition, you have to check the other axiom here. And so you have to check that the kernel of P is that. And again, it can be, I think it can check it directly, it can be a nightmare. But dissolved if not under a condition, which is that P is left or right faithfully coflat. So it's some kind of dual to faithfully flat. I won't say the definition. We don't explain it. I don't explain it, but it always holds in the case L is co-semi-simple. So,
but there is, I think, correct me if I'm wrong, but you can very easily and I think equivalently define it by this total integral of dou. I mean, if you are co-semi-simple, then I think you have integrals. But if you are just faithfully coflat, then you have a splitting here, or at least a map here, which is equivariant under L, and which is unital. And I think that's enough. If it's equivariant under L, and if it's unital, it's called the total integral of dou, and under some assumptions, I don't remember, is equivalent to being faithfully coflat. And that's everybody can understand a map going the other way.
Okay, yes.
Yeah, which is covariant with respect to, of course, coproduct on L and coproduct on H combined with P. And it's enough to choose one side, left or right.
Okay, I don't know exactly. So, okay. So, but anyway, these two assertions, it's from the work of Takeshi, which was before dou anyway. Okay. So, yes. So, in fact, yes, I still wanted to say that it holds automatically in the cosmic simple case. So, sure. For people, at the origin, I'm more, the Hopf algebras that I am more interested in are the cosmic simple one, because these are the ones coming from compact quantum groups. So here you have the condition, so you are happy with that. But here it still lets you with the first question, with the first situation, which you can have. Okay, so that's what our motivation for the question of faithful flatness over of subalgebras. And so, in view of this quotient theory question, there is really an interest for the following question. So it was asked in Montgomery's book in 1993. And the question is, are Hopf algebras always faithfully flat over their Hopf subalgebras? So it doesn't come from nowhere. But before that, there was a conjecture of Kaplansky in the 1970s that Hopf algebras should be free over their Hopf subalgebras. And in fact, it was already known not too old in algebraic group theory, the simplest example that you can find. And the function algebra on SL2C is not free over the function algebra on PSL2C. Okay, so okay, this is just for an anecdotic fact. But what is less anecdotic is that, in fact, the answer to the question in full generality is no. And it was shown by Schönberg. But this is with examples which are a bit pathological in the sense that there are problems with the bijectivity of the antipode. And so, okay, so really this comes from these problems with bijectivity. And this leaves the question widely open in the reasonable situation. So in general, there is no complete answer for reasonable Hopf algebras. So the most general question is with Hopf algebras with bijective antipode over Hopf subalgebras with bijective antipode. This one remains open. Okay, so here are a few positive answers I know. Maybe I don't know all of them, but here are some important ones. So first, the commutative case. So this is if H is commutative, so you take a Hopf subalgebra of H, and then if H is commutative, the inclusion is faithfully flat. So I already mentioned that. This is known. I don't know who is it due to. It's a result on algebraic group, which is in some kind of folklore. You don't really know who has proved it. So, but what is sure is that there is a purely Hopf algebraic proof without any algebraic geometry by Takeshi in 1972. Okay, so then there are a number of generalizations. This one is quite good. If you take only that the base A is commutative, then the inclusion is faithfully flat. Okay, so this is due to Arkhipov and Gates-Gorey, 2003. To be perfectly honest, I don't understand a single word to the proof, but it's really, they use algebraic geometry. I don't understand. But anyway, that's an existing result. Okay, other positive situation is the case if H is pointed. So pointed, this means that I didn't say what it is, but you can consider comodules, the category of comodules, and you ask that every simple has dimension 1. Okay, so this is a restrictive condition, but at least it generalizes group algebras and enveloping algebras of Lie algebras. And then H is free over A. This was shown by Radford a long time ago also. And so this holds always if H is co-commutative. This is always pointed.
If I remember correctly, pointed coalgebras stirred a lot of interest from the point of view of classification of algebras.
Yes, there has been lots of work about that because it's in fact really related with Lie theory, and the classification, even in the finite dimensional case, is related with Lie theory and Lustig small quantum groups, these kind of things, and it's been quite active area pointed of algebra.
I remember names like Hans-Jürgen Schneider and Ruszkiewicz.
Yes.
But by no means just them, yeah.
Okay. So one case with a positive answer also is when H is finite dimensional, and here you have freeness also. So this is the theorem of Nicole Zoller, 1989, and this is the true generalization of Lagrange theorem, which tells you that a subgroup of a finite group divides its order divides the order of the big group, and this is exactly the generalization of that. Okay, and more recent result, and which is also quite good. It's if you assume H to be Noetherian, residually finite dimensional, and having a polynomial identity, then the inclusion is faithfully flat. So this is by Scriabin. So maybe all these conditions look technical, residually finite dimensional. This means that the finite dimensional representation separates the points. Polynomial identity, this is something that generalizes commutative because commutative algebras always have there is always a polynomial in two variables which annihilates any element. But that's really all these conditions are really natural generalization of commutative. Of course, the Noetherian assumption drops you a number of examples, but still it's very interesting as a result. Okay, and last result which is the one that made me interested by that. It's if H is semi-simple, sorry, an S is missing here, then the extension A in H is faithfully flat. So this was proved by Kirvasi-2 in 2014. Okay, so we have all these results. Again, I don't claim to be completely exhaustive, but it gives an idea of what is known in this area. Okay, and so let me explain a bit more the result of Kirvasi-2. So I repeat it again. H is co-semi-simple. The category of comodules is semi-simple. So typically, you can imagine the Hopf algebras coming from compact quantum groups. And then the extension A subset H is faithfully flat. So, okay. So the proof of Kirvasi-2 has two steps. The first one, it shows that A is direct summand in H as an A bimodule. Okay. So there is a sub-bimodule X such that H is the direct sum of A and X. Okay, so this is relatively elementary, but it's not the kind of result if you think that it's true, you should do it, but it was not obvious to see at first sight, in my opinion. So this is there is this. That's the first ingredient. And then in his paper, from this, there are a two-page discussion where he deduced the faithful flatness result by using a very large number of references to a very large number of papers, which very categorical papers. Mm-hmm. And so my first motivation for being interested in that is that I wanted to have a proof that I could understand without the reference to 4 or 5 papers, which I did not really wanted to go into. So I just wanted maybe just to write a simple proof by myself. Yes. So that was why I was interested in that. Okay, and in fact, doing the stuff, some point you realize that you don't need all the assumption. And then this gave a new result in the setting of coideal subalgebras. Okay, so before giving the result, I recall what it is. So a right coideal subalgebra of algebra H, it's a subalgebra again, such that delta of A is contained in A tensor H. Okay, so of course, Hopf subalgebra is a right coideal subalgebra. Of course, you imagine the notion of left coideal subalgebra. And here, the main source of example, again, you start with your morphism P from H to L, and then you consider, say, the left coinvariance, like that. Okay. It's easy to check that it's a subalgebra, and in fact, it's a right coideal subalgebra. If you had taken right coinvariance, you would get left coideal subalgebra. Okay, so that's typically the construction of the standard sphere that you get, you obtain like that, and you can construct it like that. Okay, so right coideal subalgebras correspond to a class of what we can call quantum homogeneous space. Some people would say that these are quantum homogeneous space. No, I think it's too restrictive as a definition, just because you necessarily you have a character on it. So I think it's too, in my opinion, it's too restrictive to be called quantum homogeneous space, to be said the most general. But it's a class of quantum homogeneous spaces that is quite reasonable. Okay. So we have this construction, and again there is some strong interest for faithful flatness over coideal subalgebras. So in view of a more general quotient theory, just Piotr mentioned it before. So okay, I don't want to go into the detail here. And also again, because when you have a right coideal subalgebra, if H is left, say it doesn't matter, but if it is left faithfully flat, then it is projective as a left A module. Okay, so again, in this setting, faithful flatness is the same as projectivity. So it's interesting if you're interested in projective module. So it was shown by Masioka and Wigner in 1994. Okay. So it's interesting to have a faithful flatness for coideal subalgebras also. But here the situation is not that we can expect that faithful flatness holds. Even in the commutative case, there are easy examples of coideal subalgebras over which the big Hopf algebra is not faithfully flat. And again, the example I had given before, if you take the coordinate algebra on SL2 C, it's not a K, it's a C, but here you have this coideal subalgebra, say, generated by the first two variables. This is a coideal subalgebra, and it's not faithfully flat. Because again, what we said before, otherwise the map from SL2K, SL2C to C2 would be surjective. Mm-hmm. Okay, so here, even in the commutative case, we can't dream for faithful flatness. But there are still some positive results, and possibly by relaxing faithful flatness to flatness. Okay, so here is a list. It's a bit like the one of the previous one with the same people, more or less. So if H is commutative, so A is a right coideal subalgebra of H, and so if H is commutative, Masioka Wigner have shown that H is always flat. Not always faithfully flat because we have seen the result, the example before, but it's always flat. Scriabin has shown that freeness in the finite dimensional case. Again, Scriabin with the same kind of assumption as in the previous slide shows that H is flat over A. And another result, which is quite interesting, is that if H is compact, so comes from a compact quantum group, and A is a coideal star subalgebra. So here you ask moreover that it's a star subalgebra, then H is faithfully flat over A. So again, this was shown by Kirvasi too, not the same paper, and also it's a quite nice result. But the star condition prevents you the previous example, because here it's not a star subalgebra. So he has something more, but then gets faithful flatness. And again, that was a very nice result by Kirvasi too.
So when you say H is compact, you mean that this is just Voronowicz, Peter Weil, Hopf algebra of a compact quantum group, right?
Yes, it's a Hopf star algebra, if you want, which has an invariant measure, which is faithful in the sense of star algebra. So.
Could you go for a second to the previous slide, please?
Yes.
Yeah, so under the Galois condition, you have that faithful flatness is equivalent to equivariant projectivity, and then you really have an equivalence. But that's not what I wanted to say. I'm so sorry. Could you maybe one more slide? I'm confused. I wanted to there was something. Yes, that's it. Okay, because I think that this is important, and I can give you a very, very simple example. So exactly as you pointed, for many people and in many examples, I think that, Richard, correct me if I'm wrong, but I think that this quantum group Baum-Kohn conjecture is one of applications where you really have to go beyond such concept of a quantum homogeneous spaces. These are called often quotient quantum homogeneous spaces because you assume that A is a subalgebra, so there's like a quotient space if you reverse the arrows. But you can easily have that it's a homogeneous space, namely that you have like the transdirection of this ambient quantum group given by Hopf algebra H. And then you don't necessarily have that A is a subalgebra. And there's a very simple example. Take the quantum double torus. It acts transitively on the usual quantum torus, but obviously quantum torus is not a subalgebra of a quantum double torus because it is a simple algebra, it has no character.
Yes, it has no character.
Unit cannot be there, but it satisfies all other axioms of a homogeneous space. So the coaction is transitive, the fixed points are trivial, right? So that's, but that's not just for the sake of generality. It's really important in applications to have this more general concept. Sorry, I just wanted to.
No, I agree. Also, if you just simply take matrix algebras, also you could not have them. In...
Exactly. Of course. Yes. Yes. Of course. Yes. Mm-hmm.
Okay. Okay, so the result I want to discuss is the following one. So if you start, so we are in the right coideal subalgebra setting. If A is direct summand in H as the right A module, okay, then H is faithfully flat as the right A module. So at least even in the proof of Kirvasi-Tours result, this gives the weakening of this condition, which was as a bimodule. So even from this viewpoint, it's a bit of improving, but it's really, it's in the Coideal subalgebra framework. Okay, so in my title there is the notion of conditional expectation. So it's a bit why. So the condition that I is a direct summand of an H is equivalent, of course, to the existence of a right A linear projection onto A. So a right A linear map E from H to A, such that the E restricted to to A is the identity of A. So this is what the condition, what I call conditional expectation. This is more nice in the title to say that, but than to say which is direct summand. So that's okay. So that's the conditional expectation notion, and also it fits well with many contexts where there are conditional expectation with much more conditions. But okay, so that's for the vocabulary in the title of the talk. And so, as we will see, in fact, for K construction, we really use the conditional expectation. Okay, so now, so this is the result. I now will go into trying to explain how to prove it. Okay, unless there are no other questions. Okay, so now it might become a bit more technical. Okay, so there is another concept that that arises when trying to do this work also. I call this faithful flattishness because it looks like faithfully flat, but it does not. I don't know if it's equivalent or not. Maybe some specialists would tell me it's obviously equivalent, but it's not really for me. Okay, so I consider a general algebra extension, and I call this right faithfully flattish. If for any left I module M, the following map is an isomorphism. So what is it, this map? So you take here on the right, you start with M on the left, and on the right, you are inside B tensor AM. Of course, B, you see it as the right module, M is the left module, okay? And you consider the sum of tensors which satisfies this equation, okay, the equation here, just that you insert the unit of B in the middle, okay, you can do that, or you can also insert it on the left, okay, and you ask that these two guys are equal. Of course, your map here now is from M to you associate one tensor M, and then it's absolutely obvious that you are inside this space, okay? Because you just put one tensor one equals one tensor one. It's obvious that it ends. Okay. So, and the definition is that for any module, this map is an isomorphism. Okay, so quite a bit obscure, but in fact, when you and again, I'm not at all a specialist of that. If you read things about faithful flatness, this is one of the first things that is proved. This property, faithful flattishness. This is proved quite at the beginning. For example, in the book of Waterhouse on affine group schemes, he defines faithful flatness and then he proves that. So this is important in what is called faithfully flat descent theory. So which is some categorical framework within faithful flatness. So I won't speak about that. Okay, so just to say that this property, which is again, it's more technical and less natural than faithful flatness, it's well known by the people who are interested in that. Okay. And so I come back why in fact, the point is that it's enough to prove everything in our framework, but for our context, recall that we had an extension and we have assumed that there is a conditional expectation. In this context, faithful flattishness is very easy to check because so the following proposition, you take an algebra extension, you assume that it's a direct summand in Bay as a right A module, and the extension is right faithfully flattish. Okay, very simple. Here you do, in fact, if you come back to your definition, you want to come back from here to M. So it's so natural to impose something which goes from B to A. And so that's what you do. You take your conditional expectation, and then you consider the map from B tensor M to M, which does that. You apply E to X, and then you apply it to M. And you have to check that it's well defined, and that's where you need the right A linearity. And then with that, you restrict it to the image of IM, and it provides the inverse. So here, faithful flattishness, if you assume a conditional expectation, it's just very easy to check. Okay, again, to do that, you need the right A linearity of E, which is to say that you have to assume that A is direct summand in B as a right A module. Okay. Okay. So I will state it after, but I can already say it. Faithful flattishness in our context of coideal subalgebras, this will be equivalent to faithful flatness. And as we see, it's very easy to check in our framework. Okay, so now to go more into the proof, I need to speak about relative of modules. Okay, so this is Takeuchi. I already mentioned consequences of his work for exact sequences. was highlighted that faithful flatness is closely related to the structure of certain categories of modules. So generally speaking, categories of modules, you have both a module structure, a co-module structure, and compatibility condition. And okay, we will use the following one. So start with the Hopf algebra H and the right coideal subalgebra as well. So here you can consider HA plus. So you take A plus. So here, again, it's the kernel of the counit restricted to A. Then you apply, you consider the left ideal generated by A plus. And this, it is easy to check that it's a coideal in H, which means that delta of HA plus is contained into that subspace. And of course, the counit vanishes on that. Okay, this condition that it's a coideal means that we can form the quotient coalgebra. Okay, it's not an algebra in general because here you can't be sure that it's a two-sided ideal, but it's always a coalgebra, and you can consider the canonical surjection, which is a coalgebra. Okay, so we make this quotient, and we also note that it's naturally a left H module because of pi. Using pi, you put it easily a left H module structure, and in this way, it becomes a left H module coalgebra. Which means so it's a coalgebra in the category, the monoidal category of H modules. Okay, and then having done all this slightly obscure construction, we can consider the category of modules MCH. Okay, so with these kinds of categories, what is on the bottom is the modules, and on the top it's the comodules. So the objects are left H modules, left C comodules, and there is the compatibility condition that the coaction here is left H linear. So here, X, you gave it the structure of a left H module, it's okay. And C, we said that it's a left H module, so we can do the tensor product. And so, okay, this is the compatibility condition, which can be written in Swidler notation. Okay, so that's it. It's for the specialist, the Swidler notation. But okay, so in some sense, again, more categorically, the category of H module is a monoidal category. You can define the notion of coalgebra inside it. C is a coalgebra inside it, and you look at the comodules inside the category of H modules, and that's what gives this category. Okay, so there are plenty of variation beyond this kind of ideas. Okay, so this is our category, and whose structure is closely related to the question of faithful flatness. Oh, yeah. Okay, so now, okay, it's good to have this definition, but we can look at examples. So the basic examples, you have C itself or H itself, okay? But there is a general procedure of induction. If you start with the left A module M, then you can, to get H module structure, you can consider the induced module. Okay? So, well,
By the way, what is A? A is again a subalgebra of H?
A is, it's always H,
okay.
Always a right coideal subalgebra.
Yeah, okay. Mm-hmm.
Okay, so I can consider the induced module, and it has a natural comodule structure, given that what you do is that you apply your co-multiplication on the left, and then to get a secomodule structure, you can project using pi And pi, this is the surjection here. So this defines the comodule, the C comodule structure. And it's easy to check that this is compatible, and this gives you Hopf module in the previous sense. Okay, so
Oh,
that
I found another typo. Sorry, I found another typo.
Yes. Oh, yes, there is a missing one. Yes, thank you. Okay, so this defines a functor. Of course, it's obvious on the morphism. So the induction functor from left A modules to R of modules. Okay. So
yeah.
Now, if I can state now the second theorem. So again, H is a Hopf algebra, A is a right coideal subalgebra, and we consider the corresponding quotient coalgebra, as we did before. So the following assertions are equivalent. So the induction functor we have just defined is a category equivalence. The extension is faithfully flat, right faithfully flat, and the extension is right faithfully flattish. Okay. So theorem 2 proves theorem 1 because we have seen that if we have a conditional expectation, we have faithful flattishness. It was very easy, and so if everything here is equivalent, we have faithful flatness. Okay, so now, assuming theorem 2, we have proven theorem 1, and then we have.
But wait, I'm confused. But there is no assumption about direct summand, no?
No, here in this theorem there is no assumption on direct sum. No. In this theorem we just say the equivalence of the condition, and the direction condition implies this one, faithful flattishness. So if we have proved theorem 2 where there is no direct sum.
Okay. Yes. Yeah, I've got it now. So I have this direct sum and assumption in theorem 1, and then you see that faithful flattishness does the job, but you want faithful flatness, and you have it by theorem 2. Okay. Yeah. Thank you.
Okay. So now, what do we have to prove? So 1 implies 2. This is obvious because if you have an equivalence of categories, this is exact. And this is faithfully exact even. Okay, so 1 implies 2. The exact sequences are the same here and here. It just depends on vector spaces. So, okay, 1 implies 2. 2 implies 3. We said that it is true, and it's really a basic fact that people in faithful flat stuff do. Okay, so we have to prove that 3 implies 1. Okay. Okay, so now we need to prove that. So to prove that we want to prove that this induction functor is an equivalence if the extension is faithfully flattish. Okay, so as an induction functor, they often have adjoints, mostly, and the inverse equivalence, if there is one, this should be the adjoint functor in case it is 1. So a natural thing to do to prove that is to prove that it's an equivalence. It's to look if there is an adjoint, and in fact there is one without assumption here. Okay, so let's construct the adjoint functor, the right adjoint to induction. Okay, so H should, again, same assumption of algebra. A is the right coideal subalgebra, and we do the quotient coalgebra. So now if you start with an object in the category of modules, we can consider, just as we did before, the coinvariance. It's a bit like the same. So here you have your left comodule structure. So the coaction of X, it is denoted in Swidler notation in this way. And you consider the elements such that you have, this is pi1 tensor X. In C, you don't have a unit. It's not an algebra in general, but you have pi1, which plays some kind of base point. And so you can define coinvariant in this way. Okay. It's not really difficult to check that these coinvariants form a submodule. Okay. And so simply this defines the functor, the coinvariant functor, which to an object here, to a Hopf module, associates the coinvariance, and this is an A module. And so it's right adjoint to the functor L. Recall L is the induction functor. I call it L on purpose because it's in this adjunction. It is the left adjoint functor. Okay, so we have a pair of adjoint functors, and then they are associated unit and co-units. So natural transformation between the composite of the two and the identity. So the unit, it's given in this way. Okay, so you start here with a left A module. You induce it to a Hopf module, and then you take the coinvariance. Okay, and the map is just as natural as possible to M. You associate 1H tensor M. It's easily seen that it's a coinvariant in the induced module. Okay, so all this is very natural to do. And for the co-units, so here you have to start first with X, a Hopf module. You take the coinvariance, and then to go back into Hopf modules, you induce again. Okay, then you have a natural map to X, and then here again it's just simple. You make H act on X, and so this gives you the co-unit of the adjunction. So very simple maps, and then what you have to do is prove we have our pair of adjoint functors. I just rewrote the same thing here. Okay, with unit and co-unit, which are very explicit. And what we have to do is to prove that these are always isomorphisms. Okay. Okay, so we have to prove that. So before going really into it, we need the last technical stuff, which is something very natural when you think about this thing, but okay. So we will have to use canonical isomorphisms, which arise in several contexts in these kind of constructions. So for a left H module X, we can consider C tensor X, and so we can make it a left H module by using the tensor product of H module, and the left comodule just applying the co-unit, the co-multiplication of delta on the left. Okay. Okay, I denoted just C tensor X, and in this way it is a Hopf module. Okay. Now, if I start with a left H module, I can just restrict it to a left A module, and I can induce it into a H module. Okay, and so here what happens is that the canonical map, which is the one meets usually, so you take H tensor X, and then what can you do? Apply the co-multiplication. If you want to go into C, you have to project, and then here you make H2 the second tensor act. So this is the canonical kind of canonical map.
Exactly, yes.
And this is an isomorphism, and it's in the category of relative Hopf modules. Okay, so this kind of canonical maps arise in many contexts, more general or less general. It depends always on what you want to do. Okay, but this is one of the good ingredients of the proof. Okay, so to do constructing the inverse is not really difficult. You use the antipode in this kind of stuff, and you constructing the inverse is not complicated. The most complicated maybe is to check that it's well defined what you imagine to be the inverse. Okay, so you have this first canonical map, and then okay, the first part of the proof of the theorem assume that your inclusion is right faithfully flattish. Then for any left A module M, the unit map is an isomorphism. Okay. So yes, so this I could make it into one slide, but maybe it's a bit dense. So you will apply your previous canonical isomorphism. Recall that it was defined for any left H module.
Mm-hmm.
So you apply it to the induced module. Okay.
Mm-hmm.
Is that okay? So you consider it in this case. Now, if you want here to construct an inverse, so if sorry,
No, just nodding.
Okay, so you want to construct your inverse, so you take your element here in the coinvariant, and you can put it into this guy in two manners, maybe putting the first HI here, or maybe putting it here. Okay, so you compute the two, and using your definition, you see that you get exactly the same thing. Okay, just elementary computation. And so because kappa prime M, so which is this one, is injective, this gives that we have the equality. Okay, we have the equality of this guy, but we are precisely in the image of the map corresponding to when we define faithful flattishness. And so there is a unique M such that this sum is 1H tensor M. Okay, so this defines you a map. You start with this guy and you get M. This defines you a map, and it's really quite simple to check that this is an inverse to eta M. Okay, so here we have proved the 1/2 of the things we wanted to do, because recall that we wanted to prove this guy is an isomorphism and this one. Okay, so for eta M, this is done with the faithful flattishness assumption. Okay. Second proposition, which does almost all the converse part, the part for mu. So consider an object X, a relative Hopf module. So the co-unit map, without assumption, you can check that it is surjective. Without assumption. And so from this, you easily see that your functor R is faithful. Okay? And if you had the assumption that H is flat as a right A module, then mu X is an isomorphism. So here you don't use faithful flattishness for the moment, you use that flat. And okay, maybe it's not totally satisfying, but we will see that it's okay because we have the other result. Okay, so here the proof I can't give it in one slide, so maybe at the end when I have all said, I can show you, depending on what you want. Okay, so we postpone this to the end of the talk if there is enough time and people are interested. Maybe at some point you will have enough of all that. Okay, so now we can finish the proof. Recall that we have the first proposition. You assume that it is faithfully flattish, then the unit map of the adjunction is an isomorphism. The second is not as simple, but we have this lemma. It is a very elementary lemma, categorical elementary lemma, which says that if we have a pair of adjoint functors, Fg, we assume that the unit is an isomorphism, just like proposition 1 allows us to do, and that the functor G is faithful. Then the functor F preserves monomorphisms. Okay, preserving monomorphisms, in fact, it's something that I didn't say, is that when you consider your condition of flatness, in fact, tensoring is always exact on the right. There's no problem on the right, the problem is on the left. And in fact, it's equivalent to preserve the injective maps after tensoring. So here, the flatness assumption that I have here is a question of preservation of monomorphisms. Okay, so now I can put all this together to prove the result. I assume that it is faithfully flattish. The unit map is an isomorphism. I assume nothing. The functor, the adjoint functor is faithful. Okay, just like here. And then I know that automatically it preserves monomorphism. So it is flat. And then by the end of the proposition 2, μx is also an isomorphism. Okay, so we have to play a bit with all the concepts at the same time, but all the three together do the job. Okay.
So what is F in the above proposition?
So in the proposition F is L, the induction functor.
L, okay, L.
E is R, the coinvariant functor. And so we are exactly by the proposition 1, we are exactly in the case that where the counit is an isomorphism and R is faithful. It's true in general. So the lemma says us that F preserves monomorphism, which is in fact that H is flat. Okay. Okay, so modulo proposition 2, we have the complete proof. Okay, so again, I will propose that to look at proposition 2 after if people want. Okay, so application to projectivity. Okay, so I mentioned already the result of Matsuoka and Wigner. So maybe in this form, it's the most useful. You take a Hopf algebra with bijective antipode, then a right coideal subalgebra. If H is a direct summand in H as a right A module, then H is projective as a right A module. So yeah, in the statement, I can assume left or right because yes, I can consider opposite and co-opposite things. So it's not when the antipode is bijective, I can switch the things. It's not too big deal. And then if A is a direct summand in H as a left A module, then H is projective as a left A module. So maybe it's the most useful consequence. Okay. And just an example. I don't have too many examples of this situation where you have the conditional expectation. Of course, there are the case of subalgebras by the result of Kirvasi too. So there are plenty of examples from this viewpoint. But examples with coideal subalgebras where this condition are not so much. So I will give one. Okay, so I consider the algebra ASN. There are some other notation for that, but let's say that it's this one. You present it by generators UIG. So these are the matrix coefficient in the matrix vision world. Okay, so with the relations that makes the coefficient the permutation matrix. Yes, that's the correct word. You sum things on lines and columns, and then you have one. And then on lines and or columns, the elements are orthogonal in the sense they multiply two different ones and gives 0. So yes, I forgot that. Yes, all this implies that these are projections also. Okay. And so this is the coordinate algebra of Wang's quantum permutation groups, which was defined corresponding to the largest compact quantum groups acting on the usual function algebra on endpoints. Okay, so it has the Hopf algebra structure given by the canonical formulas. Okay, co-multiplication corresponding to co-multiplying matrix. Okay, so I don't recall it on the slide, but it's interesting only if n is bigger than 4. For n smaller than 3, it's the relations. There are not enough generators, so the relations make it commutative. So it's just function algebra on the symmetric group. But that becomes quite interesting Hopf algebra for n bigger than 4. Okay, so you have this Hopf algebra. And then from this, you can construct other Hopf algebras. So you start with another Hopf algebra, and you can do the free product, okay, the coproduct in the category of unital algebras. You do it n times. The n is the same as this one, okay, and then it's quite clear that it gets a Hopf algebra structure, the only one possible, such that the canonical morphism for the coproduct are morphism of Hopf algebras. So you take all these free copies, and then the free raised product of A by Sn, kind of a free version of a usual raised product. So what you do is that you take the free product of your free product n copies by the algebra of the quantum permutation group, and you quotient by two-sided ideal generated by these elements. So it's not a tensor product in general, unless n equals 2. So you decide that UKI, which lives here, commutes with the case copy of A. Okay, the K here is the same as here. Okay, and okay, you decide that these two commutes. Of course, as soon as n is bigger than 3, you don't. It's not a tensor product, but it's not a free product also, because there are very local commutation relations. Okay, all this it has a Hopf algebra structure. Okay, so for UIG it's the one, and here it's a formula for people who know semi-direct product construction. It's a quite familiar formula. Okay.
Sorry, could you remind me what this new K is? I'm confused here. This new K, what is it?
New K, it's okay. So you have all these canonical maps.
Choice of slots. Okay.
So it's the numbering of the copy.
Yeah. Okay. Yeah. Thank you.
Okay. So to define your Hopf algebra structure, you must define on each copy, and so it depends on the numbering of the copy, on the number of the copy. Okay. So okay, there is this presented like this. It's a very obscure construction, I admit. So in fact, it comes. So it's an analog of the raised product of, let's say, if you take a group H and you take the product of H n times, then the symmetric groups acts on it by permuting the factors, the coordinates, and so it's a free version of that. So it arises. I made that by studying quantum automorphism groups of graphs of copies, disjoint copies of connected graphs, and that had a natural origin, but I realized just presenting it like that it's a bit obscure. Okay, anyway, this is an algebra which has just some interest, in my opinion, at least. Okay, so here you have, of course, in your free product, you have this one, which looks to be a subalgebra. It's not obvious because there is a map, but it is a subalgebra because there is an algebra map E, a projection onto A star n. You do the co-unit on ASN, and here you just send it back to where it comes from. And so it gives a retraction. Hence, this stands as a subalgebra, okay, and also a left coideal subalgebra. Right? When you see this formula here, you see that you really stay here. So it's left. Okay. So E furnishes left and right, in fact, conditional expectation. So we can apply the result about projectivity. Then this free phrase product is projective as a left and right A star n module. Okay, this is an illustration. I suspect that it's even an algebra map here. Maybe it's a bit even too strong. It's not exactly the most the sharpest example, but at least this is one.
And can you remind me why this Reef product with ASN is a Hopf algebra?
You just check the formula are correct, or define really.
Oh, I'm sorry, you have just a definition here. Sorry. So in fact, what I want to ask is, you have it as the quotient of this algebra A star n, and now when I look at this A star n star xn, is it a Hopf algebra or not?
So, sorry, what?
Let me point to it. I'm talking about this algebra. Is it a Hopf algebra as well?
Oh yes, it's a Hopf algebra, but the quotient, you do the quotient, and it's not a quotient of algebra. This one is a Hopf algebra with the free product one, but I think that if you define this formula, there will be a problem here. So it's not it does not come from this Hopf algebra structure on the big one.
Okay.
No,
Okay. Yes. Thank you so much. Yes.
Okay, so now I don't know if maybe you will tell me what you prefer to do. I can speak of the proof of proposition 2.
Well, you have 2 minutes, so you have 2 minutes.
I have 2 minutes. So no, I don't think it's worse. Okay, it is in the. I've written the details in the slides, as you see. A bit of diagrams. It's a bit. I think we're all a bit tired, so it's better to. But you can have either on the paper or here you have a condensation of the things. So maybe it's not necessary. So you can find the paper on the archive. Okay, and since then I had some correspondence with Alex Kirvasi too, and he's proved the dual version to the theorem 1. So with the faithful co-flatness stuff, but this is made a very general categorical framework. Okay, this is much more categorical, and what I do is more elementary. But that's really what I wanted at the beginning to be elementary. Okay, so thank you very much for the invitation. Thank you.
Our pleasure. Merci beaucoup. Donc, il y a question. Any questions, Richard?
No, thank you. No, I'm fine.
Go ahead. I cannot hear you, you're muted.
I had a problem with my camera, so I was fighting a little bit with this. As a result, I muted myself. Okay, so I have 2 questions. So the first question is about your notion of faithful flattishness. It is very similar to what people call effective descent property.
Yes. So sorry, have you finished your question?
I started with some context to my question.
Yes, okay. Please finish your question.
Your notion of faithful flattishness is very close to the notion of effective descent property. So people usually use this property in descent theory for schemes. For instance, Meszabiszvili proved that this is equivalent to the notion of, to the property of purity of the algebra extension. Okay. On the other hand, this descent theory is related to monadicity. And what you are doing in your arguments based on calculations, at the end of the day, it's a property of some adjunctions, which is also the context of monadicity. So I wonder how far could be your arguments presented in purely categorical terms. So this is my question.
Okay,
you are using partly algebraic calculations and partly categorical arguments. But my impression is that in a very similar situations, in the context of this effective descent morphisms, everything reduces to category theorem and to a joint factor theorem.
Okay, that's.
Are you sure your faithful flattishness is a really new notion?
So I have. Sorry, I will answer a bit. Yes, in fact, the question of so what I call faithful flattishness. So the property is it's completely known. It's in the book, and it's one of the ingredients of faithfully flat descent, the theory of faithfully flat descent. There is no doubt about it. Okay, and also I agree with your comment. A faithfully flat descent, in fact, it's a consequence of Beck's theorem or this kind of stuff. So it's clear, I think, that there's certainly a categorical framework that could maybe do the thing better. With this kind of stuff, it's always the same thing. You can go very general and obscure. The problem is not to find the biggest generality, but maybe the correct generality for what you want to do. So I don't know. It might be. I suspect, yes, that there should be a better categorical way to do it. The point is that I would not like it to become obscure because of that. So okay, so thank you for pointing out that they call this purity. I did not know the term. I will try to look a bit at it. But if you have any reference to advise me to learn a bit more about that, I'll be happy to have them.
I have a reference to the paper of Meszabiszvili about faithful
yes
descent, faithful flat descent for schemes. Although this is in the commutative context, so I'm not sure if could be generalized to your more general framework. I have second question, if I could.
Go ahead.
To compare your theorem number 1 and Quvacitu theorem for star subalgebras. How much this star is important in Quvacitu proof, and could you draw a parallel between your proof and arguments of Quvacitu?
There is no really parallel. The point is the star condition I simplify maybe, I oversimplify maybe, but the star condition allows you to, when you do the quotient coalgebra, it allows him to show it that it has a co-semi-simplicity property. And then, because he can consider invariant scalar products on comodules, and then this gives some co-semi-simplicity. And that's what does the job that proves faithful co-flatness, in fact. And then from this, there is a general result here that if you have faithful co-flatness, you will have this. But the star really is here to consider to give some extra structure on the quotient coalgebra, a structure which is good enough to have invariant scalar product on comodules, on finite dimensional comodules.
Okay. Oh, by the way, I realized I would have another question if I could. This notion of this short exact sequence of Hopf algebras is self-dual, if I'm not wrong.
Yes.
If you had this, yeah, if you have these two conditions of commuting with a plus and equality of the left and right invariance of the collection, so they're dual one to each other. If you reverse arrows, you obtain the other. Am I right?
It looks, I don't know. I'm not always sure that it's completely dual. I think most often it is, but in the finite dimensional situation, it's sure that it's completely dual.
Yeah, this is for sure.
In general, I'm not very sure. Yes.
Mm-hmm. So I was impressed by this dual role of flatness and co-flatness in two versions of these theorems. So this raised my interest for duality, self-duality of this construction, but maybe it's not. Maybe it needs some assumptions which are not generally fulfilled for non-finite dimensional case.
It's really something that is maybe to be better understood, because in fact in the original paper of Takeshi, the category that I consider here, for which I consider faithful flatness, here he considers faithful co-flatness, and these conditions are with co-flatness. So I've not completely well extracted maybe the heart of the question. I don't know.
Okay, thank you very much.
Okay, Makoto, go ahead.
Thanks. If you look at the dual coideal for A in the dual Hopf algebra, then does this conditional expectation imply something for the dual coideal? I remember for coideals in compact quantum groups, that condition implied something like invariant weight for the dual coideal. And is there something like this?
I don't know. I haven't looked at. I haven't looked at that. So you mean the dual in the multiplier algebra sense, or the?
Yes. I guess it's going to be something like this, because the invariant weight are probably unbounded. So
well, I don't know if this condition can be. Maybe it's very simple, but I didn't think at all about it.
Yeah, thank you. Anyhow.
Okay, anybody else? I don't see any raised hands. So in this case, let us thank our speaker again. Thank you so much. Let me stop recording.